Hi. As you remember, this lecture is devoted to testing statistical hypotheses and interpreting results of such tests. And in order to analyze this topic, we shall start with normal distribution. On this graph, you can see a normal distribution where probability density is the dependent variable and x is an independent variable. Basically, it can be any variable: level of income, weight, age, and so on and so forth. So formula is pretty complicated, that's why we will analyze it step by step. First of all, f of x is the value of probability depending on the value of independent variable. It's equal to 1 over sigma times square root of 2p multiplied by e to the power of negative 1 over 2 multiplied by, in brackets, x minus mu divided by sigma. So in this equation, x is the value of variable, independent variable, and f of x is probability. So mu is simply the average value of x, so it's sum of all the values divided by the number of observations, and sigma is another measure of dispersion similar to variance. So you calculate it as the square root of this ratio. So first of all, you need to take a sum of all the distances between x and the average value of x and divide by n minus 1, where n is the same number of observations. Sounds pretty complicated. But basically, normal distribution is the very fundamental concept in statistics. It's assumed that any variable in the population has a normal distribution. Naturally, when the value of x is equal to the average value of x, the probability is maximized. Consider the following example. There is a population consisting of 10,000 people. And let's say the average value of IQ in this population is equal to 105. Just hypothetically. So if you take randomly a person, one person out of this 10,000 of people, the probability that IQ of this person will be equal to 105 will be the highest. The probability that you will pick a person with much higher level of intelligence, let's say 120, will be lower. And the same will apply for lower values. So let's say if we have 90 here, the probability will be symmetrical. We already discussed the notion of representative sample. And although we will get back to this at the end of this video, the idea is like that. All the variables in population are normally distributed. That's why if variables are normally distributed in the sample is representative. It provides true information about population. And vice versa, of course. Skewness and kurtosis are two key statistics when it comes to normal distribution. It's hard to explain what skewness is, but you can assess it as the indicator of how symmetrical the distribution is. So if skewness is equal to 0, as it is in normally distributed sample, then the distribution is perfectly symmetrical, just like this one. If it's bigger than 0, then distribution will be skewed to the left, and if it's negative, the distribution will be skewed to the right. Those are some examples I designed for you in order to demonstrate what it looks like. So you can see on this graph a function with negative skewness, it's skewed to the right, positive skewness, skewed to the left, and zero skewness, or perfectly symmetrical distribution. When it comes to kurtosis, in normal distribution, it's always equal to 3. If we increase this value, then the distribution becomes more peaked. And this is an example. So this is the distribution with kurtosis equal to 3. And in this distribution, kurtosis is equal to 10. As you can see, it's much more concentrated around the mean value. As I mentioned before, normal distribution is something you expect from the representative sample. To be more specific, central limit theorem states that the sample is representative if the variables are normally distributed. Of course, not always it's possible to achieve this. I mean, to design a sample with all the variables normally distributed. Sometimes it arises from the gaps in data when you simply do not have the data available. Sometimes, there might be different reasons. So, of course, if the variable is not normally distributed, it does not imply automatically that you cannot design a regression model with this variable. However, it might result in some biases. So it's a good practice to analyze the distribution of the variable before running a regression model. I will show you how to do this. So for this purpose, you use Gretel. I used Healthy Life Years dataset. As usual, it's attached to this lecture. You can find it in materials. I want to analyze frequency distribution. So number of beans basically specifies the degree of precision. If you add more bins, then it will be more precise. And I would like to test against normal distribution. So this black line stands for hypothetical normal distribution, which was calculated based on the values of sigma and mean. Those are relatively easy to calculate based on statistical data. And those beans stand for empirical distribution in my data set. So you already see it's pretty different. First of all, there are several peaks. Like there are a couple of sub-distributions like this one, and this one, which already suggests that my data are not distributed normally. Sometimes this results from too few observations. So if your sample is relatively small, it's really hard to achieve normal distribution of variables in the sample. Of course, when it comes to testing normality, there are more specific tests. We are going to discuss one of them at the end of this lecture. But in this case, even some brief visual analysis is enough to conclude that the data is not distributed normally. So that was it when it comes to introduction to normal distribution. I thank you, and I really hope it was helpful.